All right, let's take a look at chapter 11, and that's all about mathematics and the arts. So it's a very atypical way of looking at math, and it's probably things you've never studied before, at least in a math class. The whole point is to try to show you that we do use math outside of what you typically see math being used as. And section A focuses on music. And so if you have any experience with music, either playing an instrument or singing in a choir, if you know how to read music, a lot of these things are going to kind of be reviewed for you, but we're going to put them into a light that we can also use in our math class. So hopefully it's something you find interesting. And like I said, just a different spin on how we do use math outside of the classroom. So we're just going to start with some vocab terms, and these are specifically music vocab or sound vocab words, but they're going to be used a lot throughout this lesson. So as any vibrating object produces a sound, and the vibrations produce a wave. Also, maybe wave might be something that you've studied in a science class before, but they can particularly apply to music. Most musical sounds are made by vibrating strings, vibrating reeds, or vibrating columns of air. So depending on what type of instrument you're playing, what vibrate changes, but we're still creating the sound based on that vibration. One basic quality of sound is pitch. And the shorter the string, the higher the pitch. That's going to be the difference that we hear in a tone. It's going to be what we call our pitch. A few more vocab terms before we can get really started digging into the math behind the music. And the first is the frequency. The frequency of a vibrating string is the rate at which it moves up and down. The higher the frequency, the higher the pitch. When we measure frequency in CPSs, or cycles per second, how fast or how many cycles we have. Higher CPS means a higher frequency, which means a higher pitch. The lowest possible frequency for a particular string, called its fundamental frequency, occurs when it vibrates up and down along its full length. Waves that have frequency that are integer multiples of a fundamental frequency are called harmonies. And there's that good math vocab term, integer. And remember, integers are whole numbers and their opposites. So if it's a whole number, like 2 times the fundamental frequency, or 8 times, not 8.5, not 3.5, not 3.25, but integer values are what we call harmonies. So here's just a little picture to help kind of demonstrate this for you. A string vibrating up and down at its fundamental frequency. That's the first picture you see. And then twice the fundamental frequency, so that would be creating a harmony because it would be a multiple of 2. Notice the waves are half as long as the fundamental frequency. There's 2 waves within that entire length. And the last one is 4 times its fundamental frequency, making those waves a quarter as long as the fundamental. All right. Raising the pitch by an octave, and again, if you're familiar with music, that's going to be a term you've heard of before. If you're not, it might be new to you, corresponds to a doubling of the frequency. Pairs of notes sound particularly pleasing when one note is an octave higher than the other note. An octave is the interval between, say, middle C and the next higher C. For example, middle C has a frequency of 260 cycles per second. The C above middle C has a frequency of 2 times 260 CPS, or 520 CPS. All right, we've got one more slide of kind of vocab, and then we'll go ahead and get into some of the math behind this. A musical tone that spans an octave comprises a scale. The Greeks invented the 7-note, or what we call a diatonic scale, that corresponds to the white keys on the piano. So if you think about a piano, it's got the white keys and the black keys, and there are more white keys than there are black keys. Now, Johann Sebastian Bach adopted a 12-tone scale, which corresponds to both the white and the black keys on a modern piano. Notice, again, 12-tone versus 7-tone. So we didn't double the amount of tones we had when we added those black notes into our piano. If you think about a piano, there are sometimes white keys that are next to each other with no black key in between them. So we're looking at a 7-tone versus a 12-tone scale. On the 12-tone scale, so that's including all of the white and the black keys on a piano, 2 consecutive notes on the piano keyboard are separated by a half step. So to go from one note to the next, whether it be white to white or white to black, is a half step. For each half step, the frequency increases by some multiplicative factor. Let's call it f. In this next table, we're going to look at those values. So each time that we descend on our note scale here, we're going a half a step. Okay, so C to C sharp is half a step, C sharp to D is half a step. Now notice here we don't have an E sharp. We go right from E to F. That's still half a step. That's one of those instances I was talking about where we don't have a black key in between the E and the F on our piano keys. And notice our next column over looks at the frequency, the cycles per second. And you can see that as we move up, these are moving above middle C. As we move up, our CPSs get higher, meaning our pitch gets higher, meaning the sound we hear is a higher sound. And what they've done here is they've shown you what happens if we look at the ratio to frequency of the preceding note. And you can see that it's the same for all of these values. And that's a number that we're actually going to pull, that 1.05946, which is an irrational number, so we've had to round here. So anytime that we're using this value, we're going to have a little bit of an estimated answer since we don't have an exact value here. We're rounding just a little bit, but it's still pretty precise. And here are your ratios to frequency of middle C. You can see once we get to our octave higher at C, we're at twice as high of a frequency. And we're getting closer and closer to that 2 times as high, or doubling as we get closer to that octave above. So let's go ahead and talk about how this applies to math here just a little bit. An exponential function can be used to find any frequency on the scale. So we don't need a chart necessarily to use that to find an exponential function. And if Q naught, remember when we have a sub-zero or a subscript of 0, we call that Q naught or naught, typically meaning our beginning frequency or our beginning value. So if Q naught is the initial frequency, then the frequency of the note n half steps higher is given by this function. Our frequency, or Q, is equal to Q naught, our initial value, times f to the n. And now f is that value we just defined back here in this third column. F refers to the ratio to frequency of the preceding note, and we can go ahead and in the case of this lesson, we're always just going to go ahead and replace f with the 1.05946. And then n refers to the number of half steps higher that we're looking for. Okay, so let's go ahead and practice that. Use the exponential growth law to find the frequency of the note a fifth above middle C. Okay. So we're going to start with Q, and here's my formula. My frequency equals Q naught, or the initial frequency, times F, which we've defined to be 1.05949 to the power of n. So let's go ahead and define our variables before we can use this formula. Q naught is our initial frequency. So we're looking for a frequency a fifth above middle C. So my initial frequency is going to be that frequency of middle C. We talked about it a few slides above this table, but we can also find it right here on this table. Middle C is listed as that first note, and we have a frequency of 260. You're going to use that a lot in your homework if you just want to make a note of that somewhere on a sticky note or something, because you will be coming back to that. So Q naught is 260 CPS. Now the only variable we need in order to use this formula is what n is. Now we're looking for a note a fifth above. Notice that does not say 5 half steps. It says a fifth above. So let's go back to this chart again, this table 11.1. And notice a fifth above it is G. So what I'm looking for is the frequency of G. Now, I could just use this table, but I want to go ahead and practice doing that. So when I'm doing problems that aren't listed on the table, I can still follow this. So if we count from C to G, we need to count how many half steps that is to get to a fifth above middle C. So C to C sharp is 1, to D is 2, D sharp is 3, E is 4, F is 5, 5 sharp is 6, and G is 7. So to get to a fifth above, we're actually talking about 7 half steps. So our n value here is in fact 7. And now if we go ahead and use our substitutions for Q naught and n, we get Q is equal to our initial frequency, 260, times 1.05949. Don't round that number, leave that as is, to the power of 7. And when we do that, we get about 390 cycles per second. And that does match what our chart shows us we should get, but we're going to go ahead and find that using the formula. The last thing we want to talk about in terms of music is the changes in music as we now enter what we've called the digital age. And this is until the early 1980s, nearly all music recordings were based on the analog picture of a music. Today, most of us listen to digital recordings of music. When a recording is made, the music passes through an electronic device that converts sound waves into an analog electrical signal, which is then digitized by a computer. So you just have a little bit in your homework that kind of expands on this, so I wanted to introduce those terms to you. but just kind of a talk about how another way that we can use math, science, technology when we're talking about music. If you have any questions on the lesson, please shoot me an email.